Hi, Pokey Pencil preschoolers. We're still on Magnet Week. Today's book is Magnets Push, Magnets Pull by David Adler. This book has a lot of science experiments in it, so if you want to get some magnets and paper clips to try doing some of these with while I read, you can. A world without magnets would be a world without computers, printers, cell phones, televisions, vacuum cleaners, and microwave ovens. Yikes! It's a magnet's invisible pulling and pushing force called magnetism that helps power all these devices. It's a good thing we have magnets, huh? Magnets are attracted to anything made of iron, steel, nickel, or cobalt, and some less plentiful metals, including neodymium and samarium. There are two kinds of magnets, simple magnets and electromagnets. You are probably most familiar with simple magnets, the kind you find in toys or used to hold papers up on the fridge. Do you have a simple magnet? If you do, you can use it as a metal tester, but be careful with your magnet. Do not bring it close to a watch, clock, computer, television, or any delicate instrument. It could damage them. Be careful. Test some US coins. Does your magnet stick to any of them? It shouldn't. US coins aren't made mostly of iron, steel, nickel, or cobalt. Pennies, nickels, dimes, and quarters are mostly copper. Place your magnet on the hood of a car. Does it stick? It should. Most cars are made from steel. Take a few cans out of your pantry. Does your magnet stick to them? It might stick to some of them because some cans are made of steel and other cans are made out of aluminum. Simple magnets come in many shapes and sizes. If you have a magnet of any size, you can use it to test the force of magnetism. Look, I'm testing the force. Place a few steel paper clips on a table or a flat surface. Put the magnet on the same surface, about a foot away. Slowly move the magnet towards the paper clips. You're just moving the magnet, but the paper clips soon will start to move too. They'll slide across the table and stick to the magnet. Your magnet's invisible pulling force pulled the paper clips across the table. That's pretty cool. If your magnet is strong enough, it will work through paper, water, and glass. Place a paper clip on a sheet of paper. Hold the magnet beneath the paper. Without ever touching the paper clip, you should be able to use your magnet to move the paper clip. Drop a few paper clips in a shallow bowl of water. Then hold your magnet at the surface of the water. That means the top of it. If the magnet is strong enough, it will pull the clips right up to the top. With a really strong magnet, you would be able to hold it against the side of the bowl and move the clips to the other side. Oh, that sounds fun. You should try those. A bar magnet and some iron filings available at most hardware stores will help you understand magnetism. Cover your bar magnet with a white unlined sheet of paper. Center the paper over the magnet. Sprinkle the iron filings onto the paper and gently tap the paper. Now look at the iron filings. They should form a pattern showing the magnet's magnetic field. The pattern shows where the magnetic force is the strongest. It's strongest by its two ends, where many of the filings should have gathered. See this one? They drew a dotted line where the magnet is, and so you can see lots of iron filings right by them. And the other one's kind of scattered. Pretty cool, huh? The two ends of a magnet are called its poles. Each magnet has two poles, a north pole and a south pole. You can test your bar magnet to see which is its north pole and which is its south pole, because some magnets don't have the N and the S on it, huh? So you can tie a thin string around the middle of the magnet going lengthwise. Tape the other end to the bottom of a wooden bookshelf or table or something. The string should be just long enough to let the magnet hang freely. Be sure there's no other magnets around and nothing made of iron, steel, nickel, or cobalt. Nothing to confuse that magnet. Gently tap the magnet. When it stops moving, one pole should be pointing north and the other pointing south. Ask an adult which direction is north, and with a marker you can write an N on that end of the magnet and write an S on the other end. That way you'll know which is north and south of that magnet. Sailors, hikers, pilots, and others use compasses to help them find their way. The needle, see, this is the needle. The needle inside a compass is really a magnet. One end of the needle always points north. Look at any globe. Oh, we saw that in our other book, huh? The most northern part of the globe is labeled North Pole. The most southern part is labeled South Pole. The poles of every magnet always point north and south because the Earth is a huge magnet with a relatively weak magnetic field. Its magnetic pull is strongest at its two ends, its north and south poles. That's pretty interesting, huh? With two bar magnets, you can see how the north and south poles attract, that means they come together, and repel, that means they push away from each other. The poles of bar magnets are often marked N and S. If yours are not, you can test them by letting them hang freely, tapping them and seeing which way each pole points. Then mark both ends of each magnet with an N or an S. Just like the experiment, huh? Place both magnets on a table or any flat surface. Place them at least a foot apart and line them up with one pole of each magnet facing the other. See how the two S's are facing each other? Slowly move each magnet toward the other. What do you think is going to happen? If you have an N pole moving towards an S pole, you're going to feel a strong magnetic attraction pulling it together. The pole of one will stick to the pole of the other. Opposite poles attract each other. But these two, they're pushing it apart. The only natural magnet is lodestone, a stone loaded with magnetite, a magnetic material. All other magnets are man-made. Pretty interesting, huh? You can make a magnet. Take a large steel paper clip and hold it close to some iron filings. If the filings don't stick to the clip, you know that clip is not magnetic. But now, take your bar magnet, start with one pole of the magnet pressed against one end of the paper clip. Rub it along the clip to the other end. Do this again and again, 20 or 30 times. Rub the same pole of the magnet against the clip, always in the same direction. Now hold the paper clip close to some iron filings. Does the clip attract the filings? If it does, the paper clip is now a magnet. Do you see how they're sticking to the paper clip? So fun to see. Why were you able to turn your paper clip into a magnet? All metals are made of molecules, minuscule particles too small to see. Scientists tell us that the molecules that make up iron, steel, nickel, and cobalt are tiny magnets that are normally a jumble. See how they're all jumbled? All these little arrows are jumbled up on that. When you rubbed the paperclip, you aligned the tiny magnets until all the northern poles were pointing north. Do you see all these arrows on this? Pointing north. And all the southern poles were pointing south. With all the magnets lined up, the paperclip becomes one large magnet. That is so cool, huh? Magnets can lose their magnetic power when they are hit really hard or exposed to extreme heat. That means really hot. Magnets can also multiply. When you break a magnet in half, you create two smaller magnets, and they each will still have a north pole and a south pole. Electromagnets, sometimes called on and off magnets, use electricity to create their magnetic field. When an electric current passes through a wire, it creates only a weak magnetic field. But wrapping a wire with an electric current flowing through it around an iron rod turns the rod into a magnet. The tighter the coils of the wire, the more turns, and the stronger the electric current, the stronger the magnet. If the electric current is turned off, the electromagnet loses its power. That's why they're sometimes called on and off magnets. Pretty fun. Electromagnets are used in buzzers and bells, computers, televisions, and many other electric devices. They power all electric motors. You can't see magnetism, but you can see what it does. It's difficult to imagine a world without magnets. So many things use them, huh? That end. Thanks for reading with me. I hope you go explore with some magnets. Have fun.